this computer.
Welcome to week 3. I'm going to take these off so you don't have this weird reflection the whole time. This week we talked about datums, geographic coordinate systems, and projections. To recap last week, we went over what geospatial technology means. Those are location-based services. We described real-world applications of geospatial technology. We watched those 3 videos, one on forestry, one on bird conservation with the Audubon Society, and one on healthcare uses of GIS. We explained the difference between geospatial and non-spatial data. And really the difference is that spatial data has a location. We didn't really go over crowdsourcing and citizen science, but if you've ever edited OpenStreetMap, you've got that down. We did describe multiple applications for geospatial technology. And we did the lab 1, to demonstrate how geospatial data can be viewed using Google Earth. So this week, we're going to talk about the differences between different datums, explain how coordinate systems are measured using latitude and longitude, calculate the difference. We're actually not going to calculate the difference in time zones. Your book goes over that pretty well. We are going to talk a lot about projections. The first thing we did in class was talk about where are we and how there are different types of locations that can be obtained from your answers, just like the intro paragraph in the book. You start off at a big scale, like your town. A lot of people typed in Fitchburg, and you get smaller and smaller and smaller until you come up with a row and a column that are your coordinates. And we will get to coordinates in a little while. First, let's talk about datums. So the Earth is shaped like a lumpy space potato. Because of the combined effects of gravity and rotation, the Earth's shape is roughly that of a sphere, slightly flattened in the direction of its axis. For that reason, in cartography, the Earth is approximated by an obligate spheroid instead of a complete sphere. A geoid is the shape of the Earth's surface that the oceans would take with only gravity and rotation, without the influence of wind and tides. The surface of the geoid is higher than the reference ellipsoid whenever there's a positive gravity anomaly, and lower than the reference ellipsoid wherever there's negative gravity anomaly. And these anomalies arise from the different mass distribution of the Earth. You can see how measuring from one point gets a little complicated. So the datum is this ellipsoid that gives the base elevation for mapping. The geoid is the figure that adjusts the best ellipsoid and variation of gravity locally. It's the most accurate method, but it's used more in geodesy than in GIS. The datum is the reference point or surface against which position measurements are made. So there were 3 different datums that were described. NAD 27 is obviously the first. NAD 83 was designed from it, but the measurements don't quite match up. And WGS 84 was initially the same as NAD 83, but today there are some small differences between the coordinates. And as the Earths move and shift, you're going to end up with the coordinates moving, so they are creating a new one for 2022. We watched this short video about datums that I'll play for you now. Now that tells you a little bit about datums, and it also went into latitude and longitude. So the geographic grid divides the world into both latitude and longitude. So in the beginning, I asked, where are you located? Well, to get the most accurate answer, you have to actually ask, what are the coordinates of our classroom? One of the easiest ways to demonstrate latitude and longitude is to think about that latitude and longitude, that grid, that coordinate system grid. Let's move into projections. There are many reasons to want to project the Earth's surface onto a flat plane. Primarily to see the whole Earth at once. And also it's easier to measure distance on a flat plane rather than a sphere. Now, we're going to note that as we try to take this world and project it onto a flat surface, you're going to have some distortion. And each different projection minimizes a different type of distortion. I'll play you another video and you can see what I mean. So I happen to think that's one of the best explanations of map projections there are out there. And if you want to see how different map projections influence the size of different countries, you can go to thetruesize.com. And we played around with this a little bit in class. And you can actually see how the United States, China, and India can fit all within inside Africa. So that video went over the 3 different types of projections: planar, cylindrical, and conic. Cylindrical is what the Mercator is based on, and it gives you the most accurate size at the equator. Planar would give you the most accurate size where this plane is touching the Earth. So in this case, the Middle East. And conic is a projection where the Earth's surface is projected onto a cone and then laid flat. So in this case, it would be most accurate in size around the northern hemisphere. Now you could flip that cone over and have a different projection that works well for the southern hemisphere. This information is just background knowledge for you to absorb. The cylindrical projection for Mercator, for example, was great for nautical purposes. It was great to determine navigation because the angles and the shapes were preserved. However, the size and area of large shapes was distorted. It's not very good for world maps, but it was great to travel the Atlantic Ocean. Whereas the conic projection of something like Albers equal area preserves area, but the scale and the shape are not preserved. So it has correct proportions for area. So this would be better for something like a population map. Now this is 3 different map projections centered around this middle dot. And you can see when you're using the Mercator, it's a completely different shape and size than using something that's conic like Lambert. And then the green one is the UN projected latitude and longitude, and that also has shifted from the others based on the starting point or how it is projected onto a paper. So why is this important, right? It's important because your distance measurements on your map can be completely changed depending on which projection you use. So if you use the Mercator and you measure from LA to New York, you're going to come up with 3,000 plus miles. However, the actual distance is only 2,451. So obviously that projection is not the best. If you use something like the Albers equal area, which is a conic projection, then you end up with a distance of 2,455, which is pretty close. Nowadays we use everything digitally, so it's not as important. It's really when you make paper maps that this becomes an issue. So in summary, we talked about the different datums, latitude and longitude, and projections. In lab on Thursday, we are going to look at different coordinate systems on Google Earth. So for homework, don't forget to watch the videos, read the readings, do the weekly quiz that's based on that reading, and then submit the lab assignment. Thanks. How do I stop